All right, I'd like you all to think about some presentation you saw that left you with an impact, stirred up some strong emotions. And this is a presentation about Swift concurrency. But I'm bringing up feelings because really it's my experiences using Swift concurrency. And more specifically, my experiences using Swift concurrency incorrectly. And I cannot stress enough, I have used this thing just horribly wrong. Now, we're going to look at code. We're going to look at a whole bunch of code, actually. But when I was getting started, I wanted to think about what feeling I wanted you to leave with. And I think I want to leave you with just a little bit of fear. Maybe we'll call it healthy respect. Have you seen this before? Simple versus easy? It comes up in programming. I think it's fascinating. The idea is there are these things that are amazingly simple once you understand the concepts behind them, but getting that understanding can require a lot of work. And this compares to something that maybe it's a little bit easy to use, easy to learn, but actually comes down to being very deeply complicated. Take a look at this for loop here. What is going on? Like we're going over some array, and then we're checking the condition function on items in there, and if they pass, we're putting into another array. This is just a filter. But if you think this is easy, you try explaining this to a beginner. Now, I bring this up because I believe that Swift concurrency is neither simple nor easy. And that is not a criticism. The problem is that fundamentally, Swift concurrency is a concurrency system. And this is just a deeply hard thing to solve. I think it's amazing what Swift concurrency can do, especially considering it's really not all the way done and it's still under active development. It really can make things easier. But while I was learning about it and introducing it into my own code, I ran into a lot of problems. I mean, I cut myself on so many sharp edges. And so what I want to do with this presentation is introduce some to you, explain them, and hopefully prevent you from having the same problem. So what I did was I wrote down all the problems that I had, and I kind of sorted them from the least scary to the most scary. I needed some kind of unit to describe those things, so we're going with scared beakers here. This is the International Unit of Fear. We're starting with 1. So take a look at this. This is a class worker, and it's going to run some sort of asynchronous long-running operation. And we need to kick that off synchronously. So in the start function, we just start a task. And this is one of the first kinds of things I did. I was immediately confused. Why isn't the compiler telling me that I have to capture self? This is intentional. What's going on is the Swift team was thinking, well, the only times we really want to ensure that you capture self is when it's likely that you're going to introduce a retain cycle. And it was decided that that is not likely in this case. That has sort of had, I think, mixed results in my experience. It's true that usually tasks start and they run all the way to the beginning and then they finish, even if maybe they take a little while along the way. But if you do run into a problem, you're thinking, well, no big deal. I'll just do what I do for all closures and I'll add a weak self in there. And this does work with the slight quirk that everything on the right side of an await is strongly retained while it's running, including while it's just suspended. So this might not introduce a leak. It certainly could extend life cycles beyond where you might expect them to be. There is one other case where I think leaks can be real and happen, is with async sequence. And in that case, what you'd have is a task. It's maybe starting up some 4 await. The problem is that many async sequences are effectively infinitely long. And so while it's true in principle, this thing will finish, in practice it never actually happens, and you end up holding on to self forever. Here's another example. We've got some main actor function that's refreshing our UI in some way. And it's got to do that, it has to run some expensive and synchronous function. And so you think, well, before I used to do some async on a global queue, I'll just throw a task in there. But this does not work. This actually still runs on the main actor. I think this surprises a lot of people. And the reason why is because that task, unstructured tasks, inherit the actor context that they're starting in. So because we started on a main actor, this task will run on a main actor as well. And this can be convenient in a number of cases, but in this case, it's the exact opposite of what we want. The solution is just to throw a detached in here. And this is another API that works exactly the same, except it does not do this inheritance thing. All right, 2 scared beakers now. Let's take a look at an actor. This is a really simple actor. In fact, it does nothing at all. It just has one property, and that property is immutable. And in some other actor over here, we're referencing that value, and we're doing it synchronously. Typically, you would have to do this always asynchronously when you're crossing actors like this, but in this case, it's synchronous, and the compiler's happy as long as you do it within the same module. But this is not allowed across modules. What's going on here? Well, it's interesting. So Swift is preserving your ability to change that let in the future into a var. And I think that's really cool because you can do it without making any source, it doesn't introduce source incompatibility. However, maybe you spent a lot of time working on module A and you didn't even realize this until you got into working on module B finally. So this is definitely something worth keeping in mind. How about Swift UI? Just talking about Swift UI. Here we got some view. It's got a state object, and in the body, it is running some function on a peer that's calling some other function, main actor isolated. No problems, until for some reason you decide to change that state object into a state. And now the compiler's complaining about main actor isolation. What could possibly be going on here? Well, it turns out that property wrappers can implicitly change the global actor isolation of their enclosing type. This is super weird and has surprised so many people. In fact, it has been such a problem that I lifted this code from the Swift evolution proposal to change this. And that's coming, although right now it still works this way. The solution, of course, is to get rid of this implicit main actor isolation and instead apply an annotation either to the viewAppeared method or to the whole type. Okay, 3 scared beakers. Now we're getting into some more interesting stuff. Caching. I mean, like how hard could this be, right? Well, let's look at a counter. And it's a little bit of a strange counter in that for some reason, this counter's initial starting value is expensive to compute for some reason. So what we decide to do is when we increment, we're going to increment a delta. And then when we need that absolute count, we will just go and compute it asynchronously, and then we're going to add these values together. And we think, well, why should we do this every time? Why don't we cache that initial value in some private variable so that we can only have to do it once? And we know we're going to use this thing concurrently, and this is an actor, and actors are magic solutions to all concurrency problems, so we have nothing to worry about. But this is actually a classic example of the actor reentrancy problem. And what's going on here is get into get count, some thread goes into get count, initial is nil, so it goes and kicks off this await, suspends, and that makes it free for other threads to come into this actor and do the exact same thing. Now, in this case, it's not really a huge deal. I guess you're just kind of like doing some wasted work, but you can imagine situations where this would be a big problem. If you search online, you will find solutions to this, and here's kind of what they look like. It's a change where instead of caching the initial value, you cache a task that returns that initial value. And if you look at get count, what's happening now is that we are reading initial task or creating one and writing to it with no await in between. There's no opportunity for suspension, and so we are able to do this safely within an actor. This works, this is correct, but it does come with some disadvantages. You see, we're using task, unstructured concurrency, and this means that we are not going to participate in automatic cancellation or priority propagation. That might not be a huge deal, but if you wanted to do this, we can. We have to take a look, though, at what it even means to be an asynchronous cache. So let's model that. Let's model that with some state, and it can be in three possible states. So we have our cache is ready. That means it has a value, and it can just return it. The other possibility is we're in progress, and that means some other thread has started filling the cache but hasn't finished yet, and we now have to wait for that process to finish. This is in progress. And then the other state is nobody's filled the cache, and there's nobody waiting, so we're the first. And we're going to talk about that one right now. So in this case, the first thing we got to do is transition this state so that all future requesters will get funneled to this in progress condition. Then we're safe now to do this await. We don't have to worry about being interrupted, and we can return that value, but we still need to take care of these other potential tasks that are waiting. And we're going to do that using continuations somehow. Let's look at what we do in progress. So the first thing we need is an ID that uniquely represents this particular request. This is kind of contextual, but it can be easy or complicated depending. We now need a continuation, and we're going to get this from the built-in with checked continuation function. that gives us a continuation which is safe to escape from this closure, and we're going to associate it with this ID. And you're thinking, but wait a minute, I see this await keyword. So doesn't that mean we have to worry about actor reentrancy? And this function is weird because it guarantees that its body will be executed synchronously before it ever gets suspended. And that is very strange. That is not the way the await keyword is supposed to work, and yet this is how this function works. But with this, we're able to take care of resuming waiting continuations, but we still have to deal with cancellation. And we need to rely on yet another built-in function called with task cancellation handler. Also weird, also runs its body synchronously. But that allows us to associate the continuation with that particular ID and execute that continuation. And I have omitted all kinds of code here, but I think we can agree this is very complicated. And when I realized this, I first started thinking, there's got to be some kind of alternative. To understand that, let's look at our original incorrect implementation again. Remember, the problem is in get count, we're reading initial, we're then awaiting, and then writing to initial. So we have this suspension point in between a critical section. And if we're not using Swift concurrency, critical section, we're going to start thinking lock of some kind. But traditional locks are not safe to use with Swift concurrency. Mercifully, somebody made one that is. It's called async semaphore. And you can throw it right in there, keep code that looks much more familiar to what you'd be used to, but it even supports cancellation. This is a wonderful package, and I think it's something you should at least be aware of while you're working with Swift concurrency. Okay, we're getting to the real stuff now. Here's some code that probably can be found in every application that has ever been written. Unfortunately, with concurrency checking on, this produces warnings. And remember that in Swift 6, these warnings are going to become errors. And I'm pretty sure this is an example where those errors are rapidly going to become tears. Now, let me explain why. There's two warnings actually here. So the first one is talking about capturing self, which is unsendable. And self is just, it doesn't matter, some sort of UI-related object, typically not a sendable thing and definitely not sendable here. But it's necessary because Apple has updated dispatch queues async method to only accept a sendable closure. This is a real problem for us, and it's actually a problem in many other cases besides just updating the UI, because dispatch queues can often be used to protect mutable state that is inherently unsendable. Apple has recognized this is a problem, and so they've introduced new API called async unsafe, which is exactly the same, but removes the sendable requirement. That takes care of one warning, but there's another. It's telling us that this update UI main actor function is not being run on the main actor, but how can that be? Main is like right there. The thing to understand is that async unsafe and async, these are defined on all operation queues, not just the main instance. And Apple was not able to apply main actor isolation because of this. Fortunately, they've introduced yet more new API that we can use. And what this will do is say, okay, the compiler doesn't see this global actor isolation, but we promise that it is there. And should that not happen at runtime, this actually will crash. So with these two changes, we've now eliminated all the warnings, but we've got another problem here. Both of these APIs are brand new, only available in iOS 17 and macOS 14. I just wasn't able to deal with that. So I made a package that includes backwards compatible versions of these two APIs. You can check out here on GitHub. And I also added a whole bunch of other unsafe versions in places where I needed them, but Apple has not, at least yet, added those APIs. Okay, there's one more level 4 problem that I've run into, and it's ordering. And this is pretty fundamental to programming, so how hard could this one be? Well, to understand the ordering issues, you really have to look at what it means to be an async function. And so here's one that is not. Some work function that has a completion handler of some kind. And when you make it async, you get rid of all that, and you have just this nice, simple looking thing. But you fundamentally changed how this function works. And to understand that, let's look at the call sites. So previously, you'd call work, and it would take that completion handler, but you could call it synchronously. It gave work an opportunity to run code now, and then also run code when it's finished. But once it's async, that await keyword means you must have an async context, and that removes your ability to run code synchronously right now. This transition from sync to async is always necessary. And depending on what your functions are doing, that can end up being very perilous. So let's look at why. Some sort of timeline here, and it's a synchronous timeline of events. So before, we were calling work synchronously, and then doing some other stuff in the middle here, and then we were going to call work again. Now we've made it async, which means we can no longer call it this, but we have to use await. And to preserve the same ordering in exactly the same way, we really have to do this inside of one single asynchronous context. But there's all kinds of stuff in the middle. I mean, we could be calling all kinds of nested functions in different subsystems across modules. We could even be bouncing back and forth between Apple frameworks and our own. This can all happen synchronously, but it's just totally impractical to have a single context. So what do? You make two. And now you have a race, because the system is completely free to start and even finish task number 2 before task 1 has run. The solution here is to make this dependency explicit. So you capture a reference to the first task, and then you await it in the second. And while this does solve the problem, it kind of suffers from the same drawbacks where passing this task reference around can be just as impractical. And it might be possible, but it might be, at best, kind of inconvenient, and at worst, just not something that you can really do. Now, this is a thing you really have to keep in mind, is that when you're starting tasks and working with any kind of state or stateful system, you always have to be thinking about races. And when you're changing things, are you changing it from a situation where it needed to be run synchronously, and that was dependent, and now no longer necessary? To fix this, your dependencies always have to be explicit. It is always up to you. And it's much harder in this async world to hide that kind of dependency from callers. I have found for myself, what I really wanted was like this await keyword. I really wanted to just shove this thing into a queue so that I could control the ordering. Unfortunately, neither dispatch queue nor operation queue support this. And so I made one that does. It's on GitHub. And I have found these asynchronous queues to be at kind of ranging from incredibly convenient to absolutely essential. And I think this is another construct that you should at least be aware of. All right, here we are, maximum fear level, 5 scared beakers. This is an Xcode build setting. And what it does is control how strict the Swift compiler is about checking your use of concurrency. It has 3 levels, and the default is the lowest. And I kind of just left it that way because I figured somebody at Apple must have thought this through. And then there was Xcode 14.3 beta 1. And that introduced this weird bug that bumped this thing up from the default minimum to just 1 level up. And that introduced warnings in a whole bunch of people's projects, including my own. And that got me interested in what was going on here. So then I bumped it up to the maximum. I want to get the full picture. And I ended up with 1,600 warnings. Now, I have to be fair, some of these things were really easy to fix. You put a main actor over here, or you just throw like a sendable over there. These are no big deal. And there were some others that I resolved using some of the things we just spoke about. But there was this class of problem that was much more difficult to solve. And I want to talk about that one. And I'm going to use a protocol as an example. So here it is. Very simple. It's got one value, getter and a setter. And critically, there's no global actor isolation here. Now you're using this protocol on some class, and you discover that in order to fix other warnings, you're going to have to mark this thing main actor. But when you do that, now the compiler is complaining about your conformance. And what's happening is you've applied global actor isolation to the type, but that protocol did not specify actor isolation, and this is a conflict that is not allowed. What are your options here? Well, you could potentially add main actor to that protocol. I mean, if you look at UIKit and AppKit, Apple did this all over the place. That might be appropriate. But maybe you use this protocol in other places that are not main actor isolated, so maybe that's not going to work out. It can also be a very viral change one little thing, and all of a sudden you have to change everything. So you think, okay, the other option is apply the non-isolated keyword. This removes actor isolation, and this also could work, but you may need that. It could be that it's not safe to do this. And what's really happening here is we're discovering that we have this API that just doesn't really fit nicely with how Swift concurrency works. And that is the 5 beakers of fear issue. Right? I have found it easy to make API that is just fundamentally incompatible with Swift concurrency. And how? How did this happen? Well, the reason it happened is I had this build setting turned to the minimum. So I was building up this mental model of how Swift concurrency works where nobody was checking that I was doing it correctly. And this is dangerous because I really need you to start turning these things on so you can find the problems in your code now. And it is true that this is a little bit in flux. There's a lot of things changing, including Apple's own API. So you may uncover warnings that are either going to be fixed or maybe going to by the frameworks or maybe by the language itself. But I would rather you know about those things now so that you can come up with a plan for how you're going to address them and avoid building things that are just fundamentally not going to work. And this is going to be necessary because remember that in Swift 6, we're going from a state of no warnings at all to errors. So I think you want a little bit of early warning here. And that's it. Thank you very much.